Hello everyone, welcome to Chapter 20. As always, Dr. Varvel here, hoping to help you through this high school course. Chapter 20 is a lot of information. It might take about 4 videos, but Chapter 20 deals with electric circuits. You know, kind of the interesting thing, building circuits. If you go into electrical engineering or something like that, you will do a lot of this. And I hope you guys find this interesting. If you do, there's so much that you can learn about. So we're going to learn about circuits. We're going to learn a little bit about electromotive force. Actually, only a little bit about electromotive force, difference between AC, DC, difference between different types of circuits. Okay. First of all, there are electric devices all around you. I love this old CD mechanism image that's, now everything is on your phones, but it's everywhere. And all of these things are controlled by electric circuits and transistors and understanding whether something is a 0 or a 1, and then using that to direct charge to a certain mechanism. It's basically what drives our world. Now, within a battery, we use a chemical reaction to transmit electrons. But really anything that can transmit electrons, uh, like spinning a magnet around an electric field, different things that you can do, wind turbines, any kind of turbine, spinning a steel drum with a magnet inside and wires connected to generate electricity. Anything that has a potential difference, if you remember from the past chapters, anything that has a potential difference will cause electrons to flow from the higher potential to the lower potential. Uh, because of that, we can use that to make power. And the power that we make, we can use to move things. And we call that kind of the force that we can generate from a potential difference, the electromotive force. So the maximum potential difference across terminals is what we call as the electromotive force. So electromotive force and voltage are basically the same thing. Now I'm going to link a bunch of videos that try to explain all about electromotive force and volts, and I think they've done a good job, so I'm not going to go into it here any more than our book wants you to go into it. But basically understand that electromotive force, even though we're talking about a force, is really just the force that you could get out of a certain potential difference. Kind of like if I have a boulder on a hill and it rolls downhill, it has potential energy, and that potential energy gets turned into a force that the boulder has when it gets to the bottom of the hill. Same thing with volts. The potential difference is equivalent to the amount of force that you can get out of it on the other end. Now, remember that energy is something that we measure in joules, which is a Newton meter or a kilogram meter squared per second squared. And also know that this energy that we have is also equal to we're going to learn is a coulomb volt. So this is something we're going to learn. So we know that energy is measured in joules, and we know that charge is measured in coulombs. And we learned in the last chapter that this volt, which is the potential difference, is a joule per coulomb. And that's the same thing basically as saying energy over charge, similar to E over Q, energy per unit charge. So that was the previous chapter. So just to review for that, just linking it to electromotive force and understanding that they're basically the same thing. In a circuit, an electric field is created in the wire, directed from the positive to the negative terminals. That's just because we draw electric fields from positive to negative. That doesn't mean that that's the direction the electrons are moving. The electrons are moving from the negative to the positive. So when you have a battery, the electrons move from positive to negative. You may not remember that from electrochemistry because that would have come right after we shifted to online learning last year. But that field exerts a force on the free electrons and they respond by moving. So the potential difference allows electrons to flow. The electrons flow from negative to positive, but remember we draw fields from positive to negative. So the flow of electrons, that flow of electrons though, caused by the potential difference. So the potential difference, we've talked about before, that's volts. The flow of electrons due to that potential difference is current, which we use the letter I to represent current. And the unit for current is amps or amperes. and that is the same thing as a coulomb per second. So 1 amp, which is actually a crazy amount of current, means 1 coulomb per second of electrons. Remember, that's like 10 to the 18th electrons per second. So 1 amp will kill you. We generally talk in terms of milliamps, like most home circuits are around like 20 milliamps, 0.02 amps. So we rarely get to 1 amp. I mean, we do, but not in like common applications. All right, but an amp is a coulomb per second, or a Q, charge per second, that flows. So, and I should have deltas there. And we, unlike energy is J for joules, that was easy enough. Charge is C for coulombs. Potential is V for volts. And I often call, you'll see I call a lot of times I'll say volts when I really mean potential because I use them interchangeably. Current, which is in amperes, doesn't use the letter A because that's already taken. So current gets this letter I. So I apologize for the confusion there, but I is current or amperes. Okay? And we're eventually going to get to resistance, which is measured in ohms, but we don't use O, we use R. But current is I, and that is the amount of charge per unit time that passes through something. How many electrons pass per time? That's current. Voltage is the total potential difference. Like how many electrons do you have the potential of moving from point A to B? And then once those electrons are moving, the speed with which they move is the current. And there are some videos using, and the book uses the water metaphor, and I'll try and find some videos that do that and link them as well. Now, if the current or the charge moves at a steady rate in the same direction all the time, that's direct current, which is like batteries. But you can also generate electromotive force by just moving electrons back and forth. And that's called alternating current. So that's the AC. Direct current means you just push the electrons in one way. Now, the nice thing about direct current is that it's steady and it's generally safer than alternating current. However, because you're actually forcibly moving the electrons through the wire, they're moving through the entire length of water, DC can't be extended for long distances. Alternating current, each electron only moves back and forth. They move this way, then they move this way. So the actual wire itself can be any length wrong because you're just moving back and forth. You don't have to force the electrons through the entire length, just back and forth within the length. And that's one reason why we use alternating current now, is because you can transmit it in wires for a very long distance. Another reason is because since it goes through wires, it's easy to meter and then I can charge you for it. If we went with Tesla's idea of just sending current, direct current through space, just electrify the air with Tesla coils, which would work. It would work great for lights and stuff like that, but it wouldn't work with today's high demand computing equipments. So the nice thing is that would have made energy free because there's no way to meter the air yet. But alternating current does have its advantages in that it can go long distances and it can be metered, and it can have you can power much larger things without killing you from the amount of discharge that would happen. So let's look at how we solve current type problems. Basic problem. The current in a 3-volt battery, so 3 volt is the potential difference, of a pocket calculator. And if each of those little AA batteries is or even the small AAA batteries is 1.5 volts. And we're going to learn later that if I put them in series, the volts add. So when you have 2 batteries, if they're put in series, you actually have 3 volts. So 2 1.5 batteries equals 3 volts. So that's a typical pocket calculator 2 battery, although the TI 84s and above I think use 3, so that would be 4.5 volts. But a current in a 3-volt battery of a pocket calculator is 0.17 milliamps. See what I'm saying? Like not even 1 milliamp, 0.17 milliamps. In 1 hour of operation, A, how much charge flows in the circuit, and B, how much energy does the battery deliver to the calculator circuit? Well, if I want to know how much charge flows, charge is Q. And I know that current is a coulomb per second or a Q per second. If I know the current, which I've told you is 0.17 milliamps, so I know the current, and if I know the time, I can solve for Q, which is coulombs, and I should add that up here. Okay. So in this example, if I know seconds and amps, I just move the seconds over there. Times time, amount of time, times current, which is in amps, equals coulombs. So 0.17 times 10 to the negative third, or 0.17 milliamps. 3,600 seconds is a really good number to remember. 3,600 seconds equals 1 hour. So keep that in mind, because it's basically just 60 times 60, but it saves you a second of thinking if you just memorize 3,600 seconds in an hour. So we see here that that's 0.61 coulombs. Now energy, I've told you, is a Newton meter, but it's also joules. So energy is in joules. And if I know coulombs, which is coulombs per second, and I know potential, which is volts, which is joules per coulomb, or coulomb, or however you want to pronounce it. So a volt was a joule per coulomb. We learned that in the last chapter. And I'm now telling you that an ampere is a coulomb per second. If I take joules per coulomb divided by coulomb per second, or sorry, not divided, but multiply. If I take joules per coulomb, which is volts, times coulomb per second, which is current, so if I take volts times current, I get energy. So energy is coulombs times volts. You could write this, if you want, you could write this as IV. So IV is equal to energy. An easy way to remember that is if you're low on energy, you go to the hospital and they hook you up to an IV. They pump some energy into you. Of course, they're pumping lots of stuff into you, but they use an IV to do it, right? So current is a coulomb per second, Q over time. And that we call that an ampere. So a coulomb per second is an ampere. And we're still trying to remember all the other stuff from before. Another example, how many electrons flow through a battery that delivers a current of 4 amps, so this is some industrial level battery here, for 15 seconds. So first of all, amp is coulombs per second. So if I have 4 amps, that means 4 coulombs per second. And I have 15 seconds, so that tells me I'd have 4 times 15 coulombs. And if you remember from before, 1 coulomb is equal to 6.25 times 10 to the 18th electrons. 6.25 times 10 to the 18th. Electrons per coulomb. Remember, and it was 10 to the negative 19th coulombs per electron. That was in the previous chapter. So we've done these numbers before, but we're still going to use this conversion. 1 coulomb, 6.25 times 10 to the negative, or 10 to the positive 18th. And I can actually put this up here. 1C is equal to 6.25 times 10 to the 18th electrons. So this is basically getting us to current. We had energy. We spent some time on that. Then we learned about coulombs and charge, electric charge. Then we talked about electric potential. Now we're talking about current, which is the flow of that potential. And this potential can equate to an electromotive force that we can do work with. Now, how do we kind of map out this flow of electrons? Well, we map it out in diagrams. So first of all, I want you to understand that, remember that we said that the electric field goes from plus to minus. And it's just because of misunderstandings in the past. They thought maybe the protons moved. So conventional current is the hypothetical flow of positive charges. So if you look at this diagram and you see that the line is moving from positive to negative, the electrons are flowing the opposite direction, But the current, because that's the way it's always been done, current goes from positive to negative, just like the electric field. Okay, starts at positive, goes to negative. Okay, so conventional current is the hypothetical flow of positive charges. So it's the direction that a positive charge would flow, which is the same way we define electric fields. And it has the same effect as if the electrons. So the effect, you're still, it doesn't really matter, I guess is what I'm getting to, what direction you draw it, but just understand that conventional current we draw going the opposite direction. So the flow of current is really just the flow of electrons though. And it's not just determined by the amount of energy used to push the electrons, but it also is determined by the medium, like what are these currents being pushed through. So I have this potential difference, and I can create a circuit between these potential differences that allows electrons to flow. So I know the total possible energy that I have to flow. I know but the amount of energy that I can actually get out of it is not just due to that potential, it's also due to what it has to go through and how much what it has to go through resists. Which leads us to the last item here, resistance. Resistance is defined as the ratio of voltage to current. So how much potential you have and how that potential flows. If I take potential divided by how it flows, that gives me an indication of how resistive the material is that it's flowing through. So resistance, which can be anything, like when I draw a circuit, so here's a basic circuit, that R is representative of the light bulb itself. So that's the resistance as the electric current flows through the light bulb. So a typical circuit down here, V is the voltage source, like the battery. R is the resistance, the bulb. There's a switch, and if that switch is not on, then the circuit is not complete. And if you don't have a complete circuit, the energy cannot flow. Right? So basically the resistance is infinite if that circuit is open. And when you close that circuit, the resistance becomes based upon the wire that it goes through. Okay? And the way we relate these two, so if that hopefully resistance makes sense, the way we relate those two is through something called Ohm's law. Ohm's law tells us that the ratio of voltage to current, that ratio V over I, is constant based upon resistance. So the ratio V over I is a constant where V is the voltage applied across a piece of material and I is the current through the material. So for any given piece of material, so in this diagram, V over I is constant in the resistor, and V over I is constant in the wire because it's a different material. But every time we get a material, that V over I, whatever it is, will be constant through that entire material. Now, since my name, the way I remember this, my name, for those that don't know my first name, is Virgil, V-I-R, and you could remember it as V over I, R equals V over I, or you can just remember that V is equal to IR, Vir-Gil. And that helps me remember Ohm's law. So Ohm's law, V is equal to IR. Now to the extent that something can provide this resistance, makes it a resistor or resistor. So to the extent that a wire or device offers resistance, that makes it a resistor. A resistor is something that has that resistance. So let me do an example here, and then I'll probably pause this video and come back talking about resistivity and power, because I told you it's going to be a lot of at least 4 videos for this. The filament in a light bulb is a resistor in the form of a thin piece of wire. The wire becomes hot enough to emit light because of the current in it. The flashlight uses 2 1.5 volt batteries to provide a current of 0.4 amps. So I told you before, 2 1.5 volt batteries is the same thing as 3 volts. What is the resistance? Well, resistance is volts divided by amps. 3 volts, 0.4 amps, tells me that that light bulb has 7.5 ohms of resistance. Another example, 2 wires A and B are made of the same material and have the same diameter. Wire A is half as long as wire B. If each wire has the same potential difference, V is the same, how do their resistances differ? Same potential difference, how are their resistance difference? Since the potential is the same, the shorter wire will have half the resistance because it's half as long. It doesn't have, and think it's just it's pure relational physics. If I got to go this far, it takes this much. There can only be this much. There can only be this much resistance per piece of wire. And if I take two of these pieces of wire and put them together, it's going to double the resistance. So if I have half the wire, it's half the resistance. And that leads us to resistivity, which is where I will start the next video.